So far, we have seen in one of our previous videos that the resistance can be displayed by connecting the switch S1 to this ohm point. Now in this video and the next one, we want to see how this signal conditioning circuit can also provide us with the temperature display. Now going back, you can remember that since we are using a PT100 RTD at 0 degree centigrade, it should ideally provide 100 ohms. So at 0 degree centigrade, the RTD resistance being 100 ohms corresponds to a temperature display of 0. Now if you remember from one of the previous videos, with this ADC ICL7107, we had seen that the display was equal to 1000 times V in by Vref, and at 0 degree centigrade, if the temperature display should be 0, then this should equal to 0, which implies that V in should be equal to 0. Going back to this particular circuit, you can find that V2 is the same as V in, because V2 is the node voltage at this point with respect to ground. So V2 must be equal to 0 for the temperature display to be equal to 0 when the process is at 0 degree centigrade. Going one step forward, if you look at this portion, this is an inverting amplifier. So V2 can be represented as some gain K multiplied by V1, where V1 is the output voltage of this operational amplifier. So what we are trying to do here is that at 0 degree centigrade, if we want the temperature to display 0, we should somehow be able to make V1 equal to 0. And for that, we need to adjust a particular potentiometer, which is called as the zero adjustment potentiometer. So in the next part of our video, we will clean up this entire circuit and concentrate only on this portion, and we will go forward with the knowledge that one end of this potentiometer is at Vx volts and the other end of this potentiometer is at approximately -1 volt, arriving out of this voltage divider circuit. So let's continue with the analysis of the zero adjustment circuit. So far we have seen that this is the series combination of 1K resistance with the RTD, and the voltage drop across the 1K resistance is Vx, whereas the voltage difference across the RTD was considered as VRTD. We know that at 0 degree centigrade, the RTD should provide 100 ohms, or in other words, graphically we can say that when the RTD resistance is 100 ohms, then the temperature of the process must be 0 degree centigrade. So what are the values of VRTD and Vx corresponding to the RTD being at 0 degree centigrade? And we can easily frame them using the voltage divider concept, and we can write VRTD as resistance of the RTD divided by 1 plus resistance of the RTD multiplied by 1 volt, which turns out to be 0.1 kilo ohm, because RTD is 100 ohms divided by 1.1 multiplied by 1, this leads to 1 by 11. You can frame Vx as 1 minus of voltage drop across the RTD, and this equals to 10 by 11 volts. Now we have cleaned up the circuit and we are going to concentrate only on the zero adjustment port, which is resistance R11. If you remember from one of our previous videos, we have shown that you can always break this potentiometer into two parts. So with R11, this is a 1 kilo ohm potentiometer. We can break it up into an x kilo ohm and 1 minus x kilo ohm, and then we can observe or we can analyze only this particular portion of the circuit, keeping in mind the idea that if we want to display 0 for 0 degree centigrade, then V1 must be 0. So this is one node, and we can frame the nodal equations based on expression 1. So you have Vx minus of V divided by x plus minus 1 on this side and minus of V divided by 1 minus x, leading to a summation current going from node of value V to this particular node, which is at virtual ground. So this should be at 0 volt, and so we can frame this equation as equal to V minus 0 divided by 100. This is one equation. You can frame the other equation from the inverting adder circuit, and we have seen this previously as V1 being equal to negative of V RTD, because these resistances are same, which then leads to V plus V RTD being equal to 0, because we want to force V1 to be equal to 0 volts. So V is equal to negative of V RTD, and we have already found out what V RTD is, which is minus 1 by 11 volts for V. So with the first equation, we know the value of V, we know the value of Vx, and the only unknown is to find out the value of x. So substituting everything, we come to this equation, and then we obtain a quadratic equation which leads to two solutions. The first solution is negative and has to be discarded, and the second number must lie between x belonging to 0, 1, because the maximum value that it can go to is 1. This is a 1 kilo ohm resistance. So what this derivation shows is that if we vary the zero adjustment pot such that x turns out to be 0.5239, then this display will be equal to 0 for the RTD being at 100 ohms. In the kit, you will find that there is no zero adjustment pot, and this adjustment has been done internally in the circuit.